committee for inviting me with the opportunity to share my thoughts and experience with such a academic gathering. In this session, I will discussing an introduction to probability and theory using R software. The aim of this session basically is to explore the key concept and understand the practical application in different dimension, discuss how they can be effectively integrated into teaching research and professional practice. I hope this session will introduce, integrate and simulating. I encourage all participants to share their perspective, ask questions, and contribute to the discussion. With that, let us begin our discussion. So my today titles is an introduction to probability and theory using R software. This is a very, very important topic nowadays in every dimension. My voice is coming? Okay?
Yes, sir.
Right. So this is the first slide, basically focuses on types of distribution. And previous lecture, Mondal sir has discussed already about the distribution. But now I will discuss various distribution through the R software and their application in agriculture, in medicine, and in various sectors. Okay. And basically, types of distribution has two types, discrete distribution and continuous distribution. Basically, discrete distribution based on the random variables. Here, random variables may be two types, discrete and continuous. Under discrete distribution, I will discuss about Bernoulli distribution, binomial distribution, and Poisson distribution and geometric distribution. These all the distribution has very important role nowadays, because nowadays in AI has an important role in statistics in agriculture, every sector. And without any distribution, AI is not work. Okay. So Bernoulli distribution here under discrete distribution, Bernoulli distribution and binomial distribution are interconnected. Okay. And Poisson distribution has very important role. And prior you know about Poisson distribution. So here today you are know about Poisson distribution and deeply. Okay. And other is continuous distribution. Under continuous distribution, I will discuss about uniform distribution, normal distribution, exponential distribution. And here normal distribution has a very important distribution under continuous distribution. Okay. And discrete distribution. So discrete distribution is a probability distribution. So here you know about probability. So probability because very important. And what is probability? Probability is a measure of how likely an event is to be occur. Okay. And say for example, in real life example, in any player toss a fair coin. Okay, toss a fair coin. Probability of basically I know about probability of head. So probability of head is 1/2, 50-50 chance. Is head is occur or tail is occur. Okay, so is a probability concept. So range of probability here, that is 0 and 1. So value of probability lies between these values, that is 0 and 1. If probability of A equal to 0, that is impossible event, and probability of A equal to 1, that is certain event. Okay. So a discrete distribution, basically discrete, the outcomes, occurrence of discrete, that is, say for example, 1, 2, 3, and response in yes or no, question is true or false. So these information basically comes under discrete types of variables. Okay. And discrete probability distribution counts the occurrence that have count able to finite outcomes. That is Bernoulli, binomial, negative binomial, hypergeometric, Poisson distribution. These all distribution based on the discrete types of variable. Here discrete type of variable, how many number of members in your family. So your response is 5 and 6 and 7. So this type of information related to discrete types of variable. Okay. And now I will discuss about Bernoulli distribution, and I will already discuss Bernoulli distribution comes under the a discrete type of distribution. Okay, a Bernoulli distribution is a random experiment in which there are precisely two possible outcomes, only two possible outcomes under Bernoulli distribution, which is called failure and success, S. So these types of two outcomes based on failure and success, we can define a random variable from the sample space. Here, sample space, we consider sample space that is S and F. Here, S is the same success and F is a failure into the set of real numbers as follows. So here, X is a random variable, range of F failure that is equal to 0, and X of probability of success equal to 1. So you can see in box sample space, our sample space is S and F, and a range of S equal to X, matlab X is equal to 1 and XF equal to 0. That is failure of random variable of failure equal to 0 and random variable of success is equal to 1. And the probability mass function of this random variable, that is mathematical formulation of the about Bernoulli distribution, that is F0 equal to probability of X equal to 0, that is 1 minus P, that is probability of failure, and F1, that is P X equal to 1, this is the probability of success, where P denote the probability of success. Hence, probability mass function of Bernoulli distribution, and it is written by mathematically P ki power X 1 minus P ki power 1 minus X. Here X takes the values, only two values, 0 and 1. Here X, if X take value 0, that is probability of failure. If X takes values 1, that is probability of success. Okay. That if I tell about the definition of the Bernoulli distribution, that is random variable X. I have already discussed about random variable. So is called the Bernoulli random variable if the probability mass function is of the form. It is written by mathematically P ki power X 1 minus P ki power 1 minus X. X takes value 0 and 1. And we denote the Bernoulli distribution, that notation X follows Bernoulli distribution with parameter P. Okay. And some properties of the binomial Bernoulli distribution, that is X is the Bernoulli random variable with parameter P, that is mean, variance and moment generative function are respectively given by this form. Mu X, here mu X the mean of X, that is mean of Bernoulli distribution, that is P. Here P is the probability of success. And sigma X square, here sigma X square is the variance of the Bernoulli distribution, and it is denoted by P1 minus P. And moment generating function, here moment generating function, basically moment generating function is that function that calculate the mean and variance of that distribution. Okay, so here moment generating function of the Bernoulli distribution, that is 1 minus P plus P ki power e ki power T. And real life agriculture example in about Bernoulli distribution. Okay, seed germination study in agriculture sector. Suppose a farmer plants 100 wheat seeds. Okay, each seeds has two possible outcomes, basically germinated or not germinated. If seeds is germinated, that takes values 1, and if seeds is not germinated, that takes value 0. So above information, we can say that each seeds follows a Bernoulli trial. Basically, this structures how to formation of Bernoulli distribution. So under Bernoulli distribution, only two possible outcomes, that is 1 and 0, yes or no, failure or success. Okay. And data sets. So about Bernoulli distribution, which type of data sets has occurred? So this type of data occurs. This is first column seed number and other column is germination. So seed number, basically 1, 2, 3, 4, 5 ISI, and their corresponding germination, that is 1 seed number per germination, that is 1. 2 seed number take corresponding 0 germination, 3 1 germination, up to 5 0 germination. Interpretation, that is 1. Here 1 is a seed germinated, and 0 seed failed. If one takes the value 1, that is seed germinated, and takes the value 0, seed failed. So each observations follows Bernoulli distribution because here only two possible outcomes has occurred. This is 1 seed germinated and 0 seed failed. Okay. Why Bernoulli distribution is useful in agriculture? Basically, very important distribution. We talk about Bernoulli, binomial, but reality in Bernoulli, why type of situation? Bernoulli distribution is useful any sectors. Okay, so real life application, seed germination studies. Any researchers writes the publication based on the seed germination studies. Pest infestation, that is response yes or no, crop disease presence, fertilizer effectiveness, irrigation successes. Okay, so these are the application under Bernoulli distribution. This is the very important because in agriculture sector nowadays very applications, and each distribution has applicable. Okay, so disease in crop, 1 disease present, 0 not disease. Okay, if one number is assigned, this is present, and 0, this is no disease. Okay, and if I matlab jo hai in through the R software, so R software, this is a R software is visible or not? Hello, participants, my voice is visible coming.
Sir.
Yes, sir. Yes, sir. Audible,
Okay.
sir. Audible.
So Bernoulli distribution through the R programming. Basically, this is the R software, R Studio software. Okay, this is a 4 environment. So first environment में R programming or Bernoulli distribution. Here number of seeds n equal to 20. If you can take any values, number of seeds n equal to 20, 30, 40, depends on your choice. Okay, so n, if n take equal to 20. And probability of germination, that is P equal to 0.8. Here it is a very important concept. I have already discussed about the range of probability. Basically, range of probability lies between 0 and 1. So our probability P equal to 0.1. So I take correct values because these values lies between 0 and 1. Right? So n number of seeds n equal to 20 and probability of germination P equal to 0.8. So Bernoulli simulation, here R binom. R binom means generates Bernoulli outcomes. And I have already discussed Bernoulli outcomes, only two possible outcomes, 0 and 1. Okay. So if I will run this code, so n equal to 20. So console, R console, you can see number of seeds equal to in blue colors n equal to 20 and take P equal to probability 0.8 and germination, that is R binom. Yes.
Sir, the particular screen is not visible, sir. So I think you are only this. We are seeing this application.
Okay. Nice.
Screen.
Okay.
Yes.
Okay. Something else. Now it is visible.
Visible, sir. Yes.
Okay. Right. Nice. So first of all, I have discussed about theory of Bernoulli distribution and application of Bernoulli distribution in agriculture field. So Bernoulli distribution through the R software. This is the R Studio software. This is a free of cost software, no cost. Okay. So if R programming Bernoulli distribution, that is, if I will take number of seeds equal to 20, here n is the number of size. So seeds ka number of size. So here n is the number of seeds equal to 20 and probability of germination, that is P equal to 0.8 and Bernoulli simulation, here R binom. R binom means generate Bernoulli outcomes. Okay. If I will run, so n equal to 20, P equal to 0.8 and germination R equal to generates Bernoulli outcomes. And I will discuss before before slides. Bernoulli distribution takes only two possible outcomes, 1 and 0. So here in output section 1 1 1 0 1 1, so these outcomes basically 0 and only 0 and 1. Okay, so size equal to 1 represent Bernoulli trial. Okay, and through the you can graphical representation of the seed germination, that is seed germination study. Here red color shows failed seeds and green germinated seeds. So equal to जैसे 0 equal to fail and 1 equal to success. So यहाँ पे हुआ fail red color, so colors under मतलब failed seeds and success means green color. Okay. So this is the R through the R using R programming of the binomial Bernoulli distribution. Okay. Okay, nice. And next is the binomial distribution. Basically, binomial distribution, Mondalsal has already discussed about the binomial distribution and Bernoulli distribution. Basically, binomial distribution is a fixed number of mutually independent Bernoulli trials. That is, mutually independent Bernoulli trials means sum of Bernoulli trials. Here, Bernoulli trials means only values 0 and 1. So, sum of Bernoulli trials. Suppose these trials have same probability of success say P. A random variable X is called a binomial random variable if it represents the total number of success in independent Bernoulli trials. If I have Bernoulli trials and then I take the summation all Bernoulli trials up to n. So here total number of success is n independent Bernoulli trials. And definition of the binomial distribution, that is random variable X is called the binomial random variable with parameter P and N. Binomial distribution has two parameters, parameter P and N. If it is probability density function is of the form, it is the mathematically formulation of the binomial distribution. And in other words, we can say in the probability density function of the binomial distribution. That is f of x equal to n combination of x, probability p ki power x, 1 minus p ki power n minus x. And x takes the value 0, 1 up to n because sum of n independent Bernoulli trials. So lower values 0 and upper values that is 1. Okay, here it is very, very important concept, that is range of binomial distribution. Okay, where probability of takes value 0 and 1 between 0 and 1. I have already discussed value of probability lies between, always lies between 0 and 1. If you calculate values p equal to 1.2, that is wrong, totally wrong. Values of probability lies between only 0 and 1 is the probability of success. We will denote a binomial distribution, that is x follows binomial with parameters n, p. Okay. Criteria for binomial distribution. Binomial distribution must also meet the following three criteria. Basically, three criteria very, very important. The number of observation or trial is fixed because previous slide you can see x takes value 0 up to n. This is a fixed time interval. Okay, so here I can number of observation or trials is fixed. Okay, second number, each observation or trial is independent. Okay, and probability of success, tails, heads, fail or pass, is exactly the same for one trial to another trial. This is the three criteria for binomial distribution. Okay. And examples of binomial distribution, many types of example of binomial distribution can found in your daily life. Okay, for example, if a new drug is introduced to cure a disease, it is either cure the disease, it is successful. If your disease is cured, your experiment is successful. and your drug is not cure, so it is a failure. If you purchase a lottery ticket, you are either going to win money or you are not winning. Basically, anything you can think of that can only be a success or a failure can be represented by a binomial distribution, basically dichotomous population. Okay. And these are the real agronomy field example. Pest infestation in wheat plants. Basically, you can see on this picture, basically 4 types of different pictures related to agronomy. Pest infestation in wheat plants. Basically, this is a wheat crops. Okay. And इसमें pest infestation has occurred. Okay. Scenarios and agronomist studies pest infestation in wheat plants. So total plants observed 20. Say for example, probability of infestation 0.3. Each plant outcome, basically plant condition, infested or healthy. If plant is infested, takes values 1, and healthy plants is healthy, that is 0. Let x follows number of infested plants. So here x is a random variable related to infested plants. Okay, so x follows binomial distribution, that is n here n equal to 20 and p equal to 0.3. Interpretation possible outcomes infested plants. If 0, 5, 10, 20, 0, no pest attack. If infested plants 5 plant infested. If infested plant 10, moderate infestation. 20 is a severe infestation. If this type of data has occurred, so in this case, you can use binomial distribution of this type of data. Okay. And this basically these slides using the R software of binomial distribution. That is, if you can take number of plants n equal to 20 and probability of infestation p equal to 0.3. So generate binomial outcomes, simulate our experiment R binom. Here R binom means generate the R samples, okay, from the binomial distribution. So R binom 1, size equal to n, probability equal to p, because binomial distribution has 2 parameters, size equal to n and probability equal to p. Only here 1 equal to 1 times, only 1 times. So output of this code example, this is 6. Okay. And multiple experiment, simulate 100 agronomy trials. So result equal to R binom, that is here n equal to 100. Now I will take n equal to 100, size equal to 20 and probability equal to 0.3. That is because you has n equal to 20 and p equal to 0.3. So if you your objective is simulate 100 agronomy trials, so result equal to R binom. Here R binom basically R binom equal to 100, size 20, probability 0.3. So result आएगा आपका yes. This is screen is visible.
Visible, sir. Visible.
Visible R environment na R software.
Yes, sir. R software only.
Okay, okay. So probability of infestation in binomial distribution, because I will take n equal to 20 and probability of infestation p equal to 0.3 and simulate one experiment, only one trial. Okay. So R binom 1, size n. So if I run code p equal to 0.R binom, because R binom equal to only 6. Okay.
Sorry, sir. R software is not visible, sir. Only the slide is visible, sir.
Okay, okay. Now?
Now visible, sir. Visible. R software visible, sir.
Okay, okay. So P, if I take P equal to 0.3, probability of infestation, And our objective is simulate one experiment, only one experiment through the binomial distribution. So simple command is rbinom. Rbinom matlab here I assign the value 1 only one times and size equal to n, because size of n here, n are parameter of binomial distribution, size equal to n, probability p, and then run. P equal to 0.3 and rbinom, because I again simulate. So each simulation has different values. Okay. Now I erase this code and again I will run. So n equal to 20 and p equal to 0.3, r binom equal to 7, because here is a r means random variable. यहाँ पे here random experiment, and each simulation different types of random variable has occurred, and result r binom, this is 100. So in our console, this is the total number of observation is 100. This is a random variable because r binom, here r is the random from the binomial distribution. And if I have a histogram for this, so basically this is the histogram for the pest infested plants, okay, under binomial distribution. And x-axis, that is number of infested plants, 2, 4, 6, 8, 10, and y-axis frequency, and 2 number of infested plants. This is a frequency of 0, 5, 10, and 15. And this is the graph of binomial distribution. Okay. And I'll return the main slides. Okay. So histogram and interpretation, most values cluster near NP equal to 6. 20 multiply 0.3. This is the mean of the binomial distribution. N multiply P. Here N is the number of trials and P is the probability of success. So N equal to 20 and 0.3 equal to 6. So expected infestation patterns. And this is a graphical representation of this code, distribution of pested infected plants and number of infected plants already discussed. And if x is a binomial random variable with parameter p and n, then mean, variance, and moment generating function. Here mean of the binomial distribution, mu x, here mu is the notation of the mean. Okay, here mu suffix x, here x is the random variable for binomial distribution. So n p and sigma x square, here sigma square is the variance. If I take square root of sigma, so you the standard deviation. Okay, so sigma x square equal to np 1 minus p. This is the mean and variance of the binomial distribution. This is the mathematical formulation of mean and variance and moment generating function. And if you learn about the moment generating function, so you can calculate directly mean and variance with the help of moment generating function. Okay. And problem here, these are some problems of the binomial distribution, because different application, different sectors. Basically 80% of the people who purchase pet insurance are women. If 9 pet insurance owners are randomly selected, find the probability that exactly 6 are women. Okay, so so step 1, identify n from the problem. You basically first step, you identify n from the problem. Using our example question, n number of randomly selected items is 9. Okay, 9 pet insurance owners are randomly selected. And step 2, identify x from the problem. X is the number you are asked to find the probability for is 6. Okay, so here step 3, we have n equal to 9, x equal to 6, and probability equal to 80%. 80% of the people who purchase pet. P equal to 80% or 0.8. And Q, basically Q 1 minus P, here Q is the probability of failure. If you have probability of success P, so easily calculate probability of failure 1 minus P equal to 0.2, because probability of success 0.8, 1 minus, because total sum of probability equal to P plus Q equal to 1. So P here, P equal to 0.8, so you can easily calculate Q equal to 0.2. And this is the probability density function of the binomial distribution. And above all values put in this formula, we get fx equal to 0.176. And other problem, so simple calculation. If you have any question regarding Bernoulli distribution, binomial distribution through the R software, you can freely ask. If you have any question, participants.
Sir, what is the difference between Bernoulli and Bernoulli and binomial distribution, sir?
Basically, first of all, you understand about the Bernoulli and binomial distribution, the both of type of distribution under discrete type of distribution. First is okay. And binomial Bernoulli distribution basically takes only values 0 and 1. If x takes value 0, this is failure and success. Okay. If event is failure, so takes value 0, and if probability of success, so takes value 1. Here is that only two outcomes, 0 and 1. But under binomial distribution basically n independent Bernoulli trials. And you can easily identify Bernoulli trials means only two trials. Values takes failure and success, yes or no. Okay. If I will take some of the Bernoulli trials, you will receive the binomial trial. Okay. Basically, in simple form, Bernoulli distribution basically take only two values, 0 and 1. But binomial distribution basically general form of the Bernoulli distribution. Okay. Here under binomial distribution, we have n trials, but by Bernoulli distribution only two trials, 0 yes or no, failure success. But binomial distribution n trials. Kahani x is a random variable, takes value 0, 1, 0, 1, 2 up to n, because upper limit is n trials. Okay. Clear?
Okay, sir. Thank you, sir. Thank you. Clear, sir. Clear.
Okay. Now I will discuss about the Poisson distribution, and Poisson distribution is a very, very important role in your daily life. Okay. And a Poisson distribution is a tool that helps to predict the probability of certain events from happening when you know how often the event has occurred. Because nowadays LPG cylinder has occurred crisis. So number of Indian citizens in very large queue for the taken gas cylinder. So number of certain events for a particular time. So 10 to 12 p.m. how many number of citizens take the gas cylinders. So this is the Poisson distribution, has real life application of that situation. And in I will take another situation, that is banking and hospitals, medical sectors, agriculture sectors, everything. Okay. So it gives the probability of given number of events happening in a fixed interval of time, because 0 to t. Okay. Say 5 hours, 2 hours, 3 hours, 1 hours. Okay. And definition, a random variable x is said to have a Poisson distribution. This is a mathematical formulation of the Poisson distribution, e की power minus lambda की power x upon factorial x. Here lambda is the parameter of the Poisson distribution. Okay. And x is the random variable. So x takes value 0, 1, 2, up to infinite, where 0 lambda lies between 0 to infinite is a parameter. Here lambda is a parameter. We denote such a random variable x follows Poisson distribution with in bracket में lambda. Here lambda is the parameter of Poisson distribution. And Poisson distribution basically Simpson D. Poisson 1781 to 1840. and it describes random events that occurs rarely over a unit of time or spaces. Basically, this is the example of the Poisson distribution, crop trials, and pest infestation. This image shows aphid infestation on wheat leaves. You can see these images and two images, and this image shows aphid infestation on wheat leaves. And example, basically research question, how many aphid attack wheat plants per square meter? Here per square meter, that is specified time per square meter. Within 1 hour, within 2 hours, within 3 hours. So if this that question, how many aphid attack wheat plants per square meter? If this type of problem has occurred, so in this case, Poisson distribution can be used. Always. That situation. Per square meter, per hour, per seconds, per minutes. Okay. So these types of data often follows the Poisson distribution because events are rare, occurs randomly, occurs in fixed area or time. Because above questions per square meter, here fixed area or fixed time per square meter is specified. So if say for example, average aphid attack per plant lambda equal to 2. So average aphid attack here, average aphid attack is lambda equal to 2. Okay. And basically this is the R demonstration of the Poisson distribution. Define parameter, first step, define parameter, lambda. In R environment, lambda is written by this form, LAMBDA, lambda equal to 3. And meaning average 3 pests attack per wheat plot. Meaning of this R environment. Okay. And step 2, generate Poisson observations, because before R environment, you see about the R binom, R Bernoulli, here R Poisson. In R environment, sort command for generate Poisson observation, that is R Poisson, Poisson, that is 1, lambda. Here lambda is the parameter of Poisson distribution. And example, you can you receive example, this is 4. Okay. Step 3, simulate multiple plots. So result R Poisson. So your objective is 100 observations and lambda. So result is 3, 2, 4, 1, 3 up to 100. Meaning simulation of 100 experiments plots. And visualization through the graphical representation, that is histogram. So in R environment, sort command for histogram, that is hist, hist, bracket में result means these results. Step 3 में, and Poisson distribution of pest attacks and number of pest attacks. Okay. And this is the graphical representation of that R environment, that is Poisson distribution of pest attacks. X-axis number of pest attacks, because you assign the Poisson distribution x-axis, and y-axis number of pest attacks. Okay. Frequency. Properties of the Poisson distribution. If x is a Poisson random variable with parameter lambda, so same for previous distribution. Here mean lambda. Here beauty of that distribution, beauty of Poisson distribution is mean and variance equal. If mean of Poisson distribution is 2, so variance will be 2. Okay. So beauty of the Poisson distribution, mean of the Poisson distribution lambda, and variance also lambda. Okay. So mean is lambda and variance is lambda. So that distribution, mean and variance are equal. And that this is the moment generating function, e की power lambda, e की power t minus 1. This is the moment generating function of the Poisson distribution. And conditions for the Poisson distribution. Poisson distribution is the limiting case of the binomial distribution under the following assumptions. Because Poisson distribution limiting case है binomial distribution. Three conditions: the number of trials n should be indefinitely large, n tends to infinite. If your sample size is very large, n tends to infinite, and probability of success p for each trial is indefinitely small. Sample of size is very large and probability of success is very small. So NP equal to, here NP equal to lambda should be finite, where lambda is constant, or here lambda is rate parameter of the Poisson distribution. So Poisson distribution is the limiting case of the binomial distribution. And application of the Poisson distribution in real life, it is used in quality control statistics to count the number of defects items of any soaps. In biology, to count the number of bacteria. In determining the number of deaths in a districts in a given period by a rare disease, say coronavirus and any other types of disease, say TB and any types of fever. Okay, the number of errors per page in a typed material. In your books, number of error per page. How many number of error per page? Of that situation, here Poisson distribution will be used. Number of plants infected with a particular disease in a plot of field. Number of weeds in particular species in different field plots. So these all the types of application comes under the Poisson distribution, and that situation you can easily use in Poisson distribution of that type of application. This is a very, very real life examples of Poisson distribution. Agronomy interpretation about the Bernoulli distribution, binomial distribution, Poisson distribution. Bernoulli distribution, agronomy example, a seed germinates or fails. Yeah, if seed germinates or fail, only two possibilities. Here, seed germinate hoga or fails hoga. Under binomial distribution, number of diseased plants out of 20. Here, 20, very basically n tends to 20. So यहाँ पे number of diseased plants out of 20. Under Poisson distribution, number of pest attacks per plant. Okay, so these are the basically agronomy examples of three distributions, and these all the distribution comes under discrete type of distribution. And geometric distribution also under discrete type of distribution. Basically x represent the total number of success in independent Bernoulli trial, that random variable x follows itna. Okay, so Mondal sir already discuss about the geometric distribution. Okay, and properties, some properties, memoryless properties of this distribution. And now I will move continuous distribution. Continuous distribution, basically many types of distribution, but here we will discuss about three types of distribution: normal distribution, exponential distribution, and continuous probability distribution. A probability distribution in which random variable x can take on any values. In discrete case, only can take the values 0, 1, 2, 3, 4, 5, yes or no, failure and success. These types of information comes under the continuous discrete type of, but continuous random variable x can take or any values is continuous. Say your limit is your range is 0 to 5, so x can take value 0 under 0 to 5, so infinite values under 0 to 5. For example, an adult heights could only ever fall between the values 1 foot and 10 feet, but could be any one of the infinite values in between 5 feet or 5, that is 5.1, 5.01, 5.001, 5.0001. This is a continuous values. Okay, so basically you can understand about the discrete variable and continuous variable. Continuous probability distribution are represented by a probability density function PDF, which describes the shape of the distribution. And understanding the shape is important because it provides some information about the behavior and characteristics of the random variable being studied. Okay, so uniform distribution, basically uniform distribution type of continuous distribution. Let the random variable x, here x is a random variable, denote the outcome when a point is selected at a random from an interval A and B. We want to find the probability of an event X is less than equal to X. That is, we would like to determine the probability that the point selected from A comma B would be less than or equal to X. To compute this probability, we need a probability measure mu. Here mu is just a parameter that is satisfy three axioms of Kolmogorov, namely non-negativity, or non-normalization, countability, additivity. Okay. Hence, P probability of X is less than equal to X equal to length of A comma X, interval A comma X, given by denominator length of A comma B. This is the cumulative distribution, basically cumulative distribution function of fx equal to probability of X is less than X. This is the mathematical formulation of the uniform distribution. X minus A and B minus A. This is the probability cumulative distribution function of the uniform distribution, where A and B are any two real constants, where A is less than A is less than B, always. To determine the probability density function for with the help of probability distribution function, we can calculate the probability density function D. If I differentiate cumulative distribution function with respect to X, I will get 1 upon B minus A. This is the PDF of the uniform distribution, and range of this distribution A is less than equal to X is less than equal to B. Okay, and notation of that distribution, that is X follows uniform distribution A comma B. Here two parameters A comma B, and the uniform distribution provides a probability model for selecting points at random from an interval A comma B. An important application of uniform distribution lies in a random number generation. Properties: if X is uniform on the interval, and mean and variance and moment generating function. Mean of the uniform distribution A plus B by 2, and variance of the uniform distribution, that is B minus A whole square upon 12, and moment generating function written by this type of expression. Problem: if X has a uniform distribution on the interval from 0 to 10, then what is the probability of X plus 10 upon X is greater than equal to 7? Answer: since X follows uniform distribution, because values take 0 to 10, so X follows uniform distribution. Here A equal to A 0 and B 10. The probability density function of X is fx 1 by 10, because PDF of the probability distribution, uniform distribution equal to 1 minus B minus A, 1 upon B minus A. So here 0, A 0 and B 10. So 1 upon 10 minus 0. This is probability density function fx equal to 1 by 10 for limit 0 to 10. So my question is, P probability of X plus 10 upon X is greater than equal to 7. Equal to P X square, here X multiply X. So X square plus 10 is greater than 7X. And next probability, X square minus 7X plus 10 greater than 0. And P X minus 5, and this is a factorization of that term, X square minus 7X plus 10. So 2 factorization of that term, X minus 5, X minus 2. If X minus 3, X minus 5, I will return X less than equal to 2 or X greater than 5. So 1 minus, in other form, 1 minus P, 2 is less than equal to X is less than equal to 5. And because uniform distribution continuous, so 1 minus limit has 0 to 5, lower limit is 2 and upper limit is 5. This is the integration fx dx. Fx kya hai? 1 by 10. So put 1 by 10. So 1 minus 2 to 5, 1 by 10. And value of 2 integration 2 to 5, 1 by 10 equal to 3 by 10. 1 minus 3 by 10 equal to 7 by 10. So value of this term equal to 7 by 10. And other problem. Okay. And normal distribution has a very important distribution for continuous case. History of normal distribution. Basically, the normal distribution was first discovered by D. Moore, English mathematician, in 1733 as a limiting case of the binomial distribution. And a continuous random variable X is said to follow normal distribution with mean mu and standard deviation sigma. Here standard error is sigma, not variance. Okay, it is probability density function and is as follows. This is the mathematical formulation of the PDF of the normal distribution equal to 1 by sigma. Sigma here, sigma is the standard deviation. It's 2 pi, square root of 2 pi, e की power minus 1 by 2, x minus mu का upon sigma का whole square. Here x random variable, mu mean, and sigma is the standard deviation. And range of the x random variable minus infinite to infinite, and range of mean minus infinite to infinite, and range of standard deviation 0 to infinite. That is sigma greater than 0. The mean, mu, and standard deviation sigma are called the parameters of the normal distribution. The normal distribution is written by as follows: normal distribution with parameter mu, comma sigma square. Here sigma square is the variance. Condition for the normal distribution. Normal distribution is a limiting form of the binomial distribution under the following condition. If n, the number of trials, is indefinitely large and tends to infinite, neither p or nor q is very small. P and Q very small. Normal distribution can also be obtained as a limiting case from the Poisson distribution. This is the beauty of the normal distribution. With parameter m tends to infinite. Constant of the normal distributions are mean, mu equal to mean, and variance sigma square, standard deviation sigma. Basically, no, here this is the normal probability curve. Okay, this is the bell-shaped curve. A normal distribution, this is mu bell-shaped curve, and mostly values lies of that interval, okay, of the normal distribution curve. And plots of the PDFs of the normal distribution if mean 0 and sigma square variance. So this type of graphs shown. And properties of the normal distribution: the normal curve is bell-shaped and symmetric, x equal to mu, and mean, median, mode of the distribution or concave. Mean equal to median equal to mode of the normal distribution, and it is only one mode, x equal to mu. Okay, and quantization standard normal distribution, and sir already discussed about the standard normal distribution. If I will take mu equal to 0 and sigma equal to 1, that normal distribution convert to standard normal distribution. That is standard normal distribution with mean 0 and standard deviation 1. That is Z follows normal distribution at 0, 1. This is the form of the standard normal distribution. And PDF of this distribution, that is 1 upon root 2 pi e power minus 1 by 2 Z square. Because here I take mu equal to 0 and variance equal to 1. And this is the real life examples in agriculture sector. Basically, 4 types of images: A image, B, C, D. Okay, these images show agronomy experimental wheat plots where researchers grow wheat under controlled treatment such as fertilizers, levels, irrigation methods, or different varieties. Say, for example, fields are divided into small plots. Each plots receive a different treatment. Yield from each plot is measured separately. Here, very important note: researchers harvest each plot and measure grain weight per plot using the precise balances to compare treatments. And this type of problems comes under the normal distribution. In agronomy experiment, wheat is grown in replicated plots. Grain from each plot is harvested, dried, and weighted. Yield is recorded in gram per plot or kg per hectare. Typical yield data recorded in experiment: plot 1 yield 48 kilogram per plot, plot 2 52, plot 3 46, and plot 4 55, and so. This type of continuous measurement commonly follows a normal distribution, where most plots produce yields close to the mean. Okay. Suppose an agronomist studies wheat yield in 100 experimental plots. So mean yield equal to 50 kg per plot, and standard deviation sigma equal to 10, because your experiment 100 experimental plots. So square root of 100. So you easily calculate sigma square root of variance, that is 10, and random variable x, and in this case x denotes the yield per wheat plot. And then yield follows a normal distribution, x follows normal distribution, with mean 50 and variance 100. Okay. So mean mu comma sigma square. And this is the R implementation. Okay. R implementation, mu equal to 50, mean of the normal distribution, and sigma standard deviation 10, meaning average wheat yield 50 kg and standard deviation 10 kg. Step 2, generate simulated crop yield data. So yield equal to R norm. In this case, in normal case, generate R samples, basically R norm. R norm means random number generation from normal distribution. R norm. 100, mean equal to mu, and standard deviation sigma. So output is 50.53, 47.8, 60.2, and 39 point something. So these values represents crop yield from 100 experiments per hour. Okay. And step 3, summary statistics. If your need is calculate mean of yield, so in short command in R, mean bracket में yield means yield, and mean bracket में yield and standard deviation yield. Example output क्या होगा? Mean equal to 49.8 of that problem and standard deviation 9.7. And the graphical representation of that problem, that is histogram, and short command for histogram in our software HIST yield equal to this, and histogram आप देखेंगे histogram. Okay, 1 minute. This is a R environment. Okay, and okay, and mu equal to 50 and sigma equal to 10, yield equal to 100 number generation, and yield equal to 100 observations. Rounding the mean basically your mean is 50. So all random number around the 50, say 58.38, 56, 74 something, and mean is 49.97, standard deviation 8.816, and histogram of that distribution is yield kg and frequency. So you can see this from this graph is a bell shape curve. Okay, so graph of the normal distribution. Okay, okay. Histogram representation, this is the graph of the normal distribution. Okay, and this is the Z table, very very important. And continue. Most problem है ये normal distribution का. First problem, most graduate schools of business require application for admission to take the graduate management admission council GMAT examination. Scores on the GMATs are roughly normally distributed with a mean of 527, that is mu, and standard deviation, that is sigma, of 112. What is the probability of an individual scoring above 500 on the GMAT? So normal distribution, Z equal to x minus mu upon sigma, Z score. So here mu equal to 500 and x here x equal to 500 and mu equal to 527, mean of the normal distribution 527 upon sigma equal to 112, standard deviation of 112 equal to minus 0.24107. So probability of x greater than 500. Question क्या कह रहा है? What is the probability of individual scoring above 500? Above मतलब greater than. So probability of x greater than 500, that is probability of Z. Because if I will subtract x minus mu upon sigma and 500 minus mu upon sigma, so this convert Z score 5. Probability of Z greater than minus 0.24. 1 minus 0.0452, that is value 0.59. And this is the simple graph of that problem. Okay, and another problem. Here, exponential distribution. Okay, exponential distribution is frequently used to provide probabilistic answer to questions such as this type of problem. You can easily use exponential distribution. How much time will elapse before an earthquake occurs in a given region? How long do we need to wait until a customer enter our shop? How long will it take before a call center receives the next phone call? How long will a piece of machinery work without breaking down? All these questions concern the time. We need to wait before a given event occurs. If this waiting time is unknown, it is often appropriate to think if it is as random variable. Okay, so this is a waiting time. So this is the PDF lambda e to the power minus lambda x of the, here lambda is the called rate parameters. Okay, and that is the properties mean and variance and moment generating function, distribution, memoryless properties. Okay, thank you. Participant, if you have any questions, you can ask. Okay.